Alright, so this video is going to cover the very short unit that we're on right now, equilibrium and reverse reactions for pre-ACE chemistry. I'm going to focus on this first part. There are only 3 parts. These 2 are much simpler and straightforward. This is covering the bulk of the content that we're going to be talking about this unit. So these are what I want to cover. We're going to talk about equilibrium, what it is and what it is not. Some people get really confused about equilibrium as a concept when they first learn about it. If you ever see me write RXN, that's just short for reaction. We're going to talk about reversible reactions, how they work, and how we can affect them, particularly in regards to how changing the temperature, the pressure, or the concentration can affect reversible reactions. And then we're going to talk about specifically the reversible reactions of copper sulfate and water, and then cobalt chloride and water. Not these 2 reacting together, just what each of these does with water. So first, let's talk about what equilibrium is. So when you see these arrows, that means that the reaction is going forward, so sulfur dioxide reacting with oxygen, forming sulfur trioxide, while at the same time, there's some other sulfur trioxide breaking down into sulfur dioxide and oxygen. That's what a reversible reaction is. Some reactions go one way, some reactions can be reversed, and it's happening simultaneously. So that's what a reversible reaction is. Now, eventually, these reactions will start going at the same rate. That's what we call equilibrium. Now, do not be confused though. If I were to give a visual demonstration of what equilibrium is, imagine 2 boxes. These boxes are going to trade these little dots. Okay, so we've got this box giving 2 dots over to this box, and this box at the same time giving 2 dots over to this box. So they're trading equally, okay? That is what equilibrium is. It's this equal trade. Equilibrium is not the 2 boxes having the same number of dots. That's not equilibrium, okay? In equilibrium, one side might be more favored than the other. So which side has a higher concentration of dots? Have a little Dora the Explorer moment. Yes, it's the one on the right. Okay, so again, equilibrium is just in a reaction when these guys are reacting with each other to form this guy at the same rate this guy is breaking down into these 2. Okay, so they're going forward and backward at the same rate. Okay, that's what equilibrium is. Now, if this guy is constantly losing 2 and gaining 2, is this concentration ever going to change? No, because we might have given 2, but we get back 2 at the same time. So at equilibrium, the individual concentration of the forward and reverse reactions, it won't change, okay? If this is the equilibrium that we're at, then we will always have this concentration unless we change something. Okay, that's what equilibrium is. Now, what equilibrium is not, again, it's not these 2 having the same concentration or the same volume. That is not what equilibrium is, okay? Another thing that you need to know, it's something called the position of equilibrium. Position of equilibrium. That basically just means which side is this reaction favoring right now, forward or reverse? Which side has a higher concentration? The forward reaction. So we would say the position of equilibrium favors the forward reaction, okay? So that's essentially what equilibrium is, what it is not, and the position of equilibrium and reversible reactions. All very simple concepts. You just have to think about it for a second and you'll be fine, okay? So again, equilibrium. It's not both sides having the same volume or the same concentration, no. Equilibrium just means that our forward reaction and our reverse reaction are going at the same rate, okay? So that covers what equilibrium is as a concept and what reversible reactions are. All right, so already we're over halfway there. Something about Bon Jovi. Next, I want to talk about how temperature, pressure, and concentration can affect equilibrium. So basically what we're talking about is, remember how I was saying the position of equilibrium is whichever side is favored in the reaction? Well, we can actually change that. So some of you might have noticed that I wrote this little number over here. That number indicates this forward reaction has a net release of energy. Do y'all remember from the previous unit, is the forward reaction endo or exothermic? Is it taking in heat or is it releasing heat? Yes, it's exothermic. So we would say the forward reaction is exothermic. And this is true for all reactions. One of the reactions will always be exo, and the other reaction will always be endo. Now, do not be confused. This doesn't mean that every forward reaction is exothermic. That's not what that means. Just if one of them is exothermic, one of them is endothermic. Now, you may be wondering, okay, but why does that matter? Well, let me ask you this. We just talked about how temperature can affect the position of equilibrium. So which reaction likes to take in heat? Endothermic or exothermic? Endo, right? Endothermic likes to take in heat. So let me ask you this. If I were to raise the temperature of this reaction, which side do you think would end up being favored? The forward reaction or the reverse reaction? So we have forward exothermic reaction, reverse endothermic reaction. So if I raised the temperature, what would you expect to happen? Yes, okay, it would eventually, this would change up for a second, but then it would balance out. It would eventually favor the reverse reaction because this reaction, endothermic, likes to take in heat energy. So if we raise the temperature, we can shift the position of equilibrium towards our endothermic direction. So again, what do you think would happen if I lowered the temperature? Okay, if I lowered the temperature, which side would the position of equilibrium favor? If I made it cooler? Yes, okay, we would shift the position of equilibrium towards our forward reaction, okay? So that specifically is how temperature affects the position of equilibrium. Because remember what I said, you need to know how temperature, pressure, and concentration affect the position. So we just talked about how temperature affects reversible reactions based on endo and exo. If we raise the temperature, it's going to favor the endothermic direction. If we lower the temperature, it's going to favor the exothermic direction. Next, what I want to talk about is pressure. Pressure, in terms of reversible reactions, you're only concerned about pressure when you're talking about gases, and it's actually really easy. So with pressure, all you have to do, trying to erase all these dots. Let's see if I can do it. Ah, dang it. So pressure is actually really easy. All you have to do is count up the moles on each side of your gases. So we have 2 moles of this gas, 1 mole of this gas, and 2 moles of this gas. Now I'm going to throw something hard at you guys. What's 2 plus 1? Cool, 3. Now which is bigger, 3 or 2? Cool, this side's bigger. Now the reason I'm getting to that is this is how you determine how pressure will affect it. So you guys know what happens when you squeeze a tube of toothpaste. What happens? It goes out. Well, the reason that is because in a pressured system, areas of high pressure want to move to areas of low pressure. Okay, so it's kind of like if you're in a really crowded room, you want to get to a less crowded room because you hate people, right? Yeah, exactly. They're done faces and they don't put on deodorant. But anyway, what I'm saying is all you really need to know is that pressure, how it affects reversible reactions when you have gases. Basically, it's going to favor the side with fewer moles of gas when you raise the pressure. Okay, so when we raise the pressure in this reaction, it would favor which side? Which side has fewer moles of gas? Our forward reaction has fewer moles. So if we raise the pressure, it's going to favor the forward reaction. And the reverse is also true. So if I lower the pressure, which side would you expect to be favored? The reverse reaction. Very good. Okay, so that is simply how pressure affects the position of equilibrium. Again, it's affecting the position of equilibrium. So it's still going to be at equilibrium. We're just going to end up favoring one side or the other. Okay, so an increase in temperature, an increase in temperature is going to favor endothermic. A decrease in temperature is going to favor exothermic. An increase in pressure is going to favor the lower mole count, and a decrease in pressure is going to prefer the higher mole count. The last one is pretty easy, concentration. Just if we increase the concentration of something, how is it going to affect the reaction? Basically, if you increase the concentration of one thing, it's going to favor the opposite side. So if I add more sulfur dioxide, the position of equilibrium is going to favor the forward reaction because everything likes to balance out. So essentially with concentration in a reversible reaction, whichever side you're increasing the concentration on, the position of equilibrium is going to favor the other side. So if I increase the concentration of this, the position of equilibrium is going to favor the forward reaction. Okay? Just like if I increase the concentration of this, it's going to favor the reverse reaction. Okay? So that covers equilibrium, what it is not, reversible reactions, how temperature, pressure, and concentration affect the position of equilibrium. Lastly, what I want to cover with you guys is copper 2 sulfate and cobalt 2 chloride. It's really simple, just heat essentially. So this is your cobalt chloride hydrated. Now when we say hydrated, it's not that it is chemically fused or whatever. It's not like the water is physically attached so much. It's more like they have a sort of like a light bond, we'll say. It's hydrated, so it has a very weak interaction with water here. And it can do a reversible reaction where we can just completely separate it from the water. So in this form, when it's hydrated, it's kind of like a blue powder when it's hydrated. So kind of like, you know how the color of paper changes when it's wet? It's kind of what's going on here, okay? And then we can make it a white powder with water. We can make this reaction go either way if we add water. So if we increase the concentration of water when there's cobalt chloride present, what did we just say, how concentration affects it? Yes, okay, it's going to favor the hydrated direction of the reaction, okay? Now, if I said that this forward reaction was endothermic, this reaction was exothermic, if I heated up my hydrated cobalt chloride, how would you expect the position of equilibrium to change? Yes, when you heat up the hydrated metal, understandably, the water evaporates away, and so we end up going in the forward direction. That's basically all you need to know for this first a third of the unit. That's it. These other two, really short. You're going to learn about the Haber and contact process. So again, equilibrium, what it is and what it is not, okay? It is an equal forward and reverse reaction rate. It is not both sides having the same volume or both sides having the same concentration. Their individual concentrations will remain constant because they're constantly going forward and backward, but their concentrations are not going to be equal to one another. You need to know how temperature, pressure, and concentration affect the position of equilibrium, and you need to know how we can use heat and the addition of water to affect the reversible reaction of hydrated copper 2 sulfate and hydrated cobalt 2 chloride. All right, pretty simple stuff. I believe in you, but yeah, that's it.